forces of nature have been outsmarting the materials we use to build our infrastructure since we started producing them. Ice and snow turn major roads into rubble every year. Foundations of houses crack and crumble in spite of steady construction. In addition to the tons of waste produced by broken bits of concrete, each lane mile of road costs the US approximately $24,000 per year to keep it in good repair. Engineers tackling this issue with smart materials typically enhance the function of materials by increasing the amount of carbon, but doing so makes materials lose some mechanical performance. By introducing nanoparticles into ordinary cement, Northwestern University researchers have formed a smarter, more durable and highly functional cement. The research was published in the journal Philosophical Transactions of the Royal Society A. With cement being the most widely consumed material globally, and the cement industry accounting for 8% of human-caused greenhouse gas emissions, the researcher turned to nano-reinforced cement to look for a solution. Nanomaterials reduce the carbon footprint of cement composites, but until now, little was known about its impact on fracture behavior. Traditional fracture testing, in which a series of light beams is cast onto a large block of material, involves lots of time and materials and seldom leads to the discovery of new materials. By using an innovative method called scratch testing, the research team efficiently formed predictions on the material's properties in a fraction of the time. The method tests fracture response by applying a conical probe with increasing vertical force against the surface of the microscopic bits of cement. It requires less material and accelerates the discovery of new ones. Predictions formed through scratch tests also allow engineers to make changes to materials that enhance their performance at the largest scale. In the paper, graphene nanoplatelets, a material rapidly gaining popularity in forming smart materials, were used to improve the resistance to fracture of ordinary cement. Incorporating a small amount of the nanomaterial also was shown to improve water transport properties, including pore stature and water penetration resistance. Implications of the study span many fields, including building construction, road maintenance, sensor and generator optimization, and structural health monitoring. By the year 2050, the United Nations predicts 2/3 of the world population will be concentrated in cities. Given the trend toward urbanization, cement production is expected to skyrocket. Introducing green concrete that employs lighter, higher performing cement will reduce its overall carbon footprint by extending maintenance schedules and reducing waste. Alternately, smart materials allow cities to meet the needs of growing populations in terms of connectivity, energy, and multifunctionality. Carbon-based nanomaterials, including graphene nanoplatelets, are already being considered in the design of smart cement-based sensors for structural health monitoring.